I'd like to talk just a little bit about fundamental properties of matter. And properties of matter are only describing the matter that we see around us. And if you've done any research into dark matter and dark energy, you realize that the matter and energy that we know of represents a small part of what the universe offers us, but it's what we can touch, feel, smell, taste, etc. So that's oftentimes what we talk about in physics at this level. So, talking about the matter that we can do all this touching and feeling of, and tasting and smelling, etc., that there are a few very fundamental properties of that matter, and one of the properties is mass, and that's a measure of how much stuff there is, and the units for mass are kilograms in the world of physics that we normally work in. When you start doing chemistry sorts of things, you oftentimes talk about grams, which is a thousandth of a kilogram. In the world that many people exist in, that mass and weight kind of get conflated, that they are talked about in the same sort of breath. And so if you're in Europe and somebody asks you how much you weigh, you might talk about how many kilos you weigh, which is an inappropriate kind of answer, because weight is a measure of the gravitational interaction between masses. And yeah, specifically for us, it's between our mass and the mass of the Earth. And there is a constant that we know that every kilogram of mass has a weight of 9.8 newtons. And so the gravitational constant on the Earth is 9.8, or call it 10 newtons per kilogram. And so, that weight and mass are related to each other, but they're not quite the same thing. Weight is not fundamental, because you can be weightless, but you couldn't be massless. So if you wanted to lose weight, I could take you and drop you off in deep space where you were not having any net gravitational interactions with anything, and so you wouldn't have any weight. You'd be, quote, weightless, but that wouldn't change your mass. So usually people don't really want to lose weight, they want to lose mass. So mass is one of those fundamental properties, and it's a measure of how much stuff there is, if I can use a technical term like that. So there's mass, and then that mass occupies some kind of space. So you can look at there being this sort of relationship, and oftentimes that we see that mass and how much space something takes up are related through something that's not fundamental per se. It's derived, but that's in terms of density, because that you can have a certain mass of feathers and a certain mass of lead, and they won't occupy the same amount of space. But how much space something takes up, what volume it occupies, is something that is fairly fundamental. And the one other primary fundamental feature or way of describing uh, matter as we know it is in terms of charge. And so if you look at the screen, you've been seeing this is an artist's rendition of what a black hole looks like. And without going deeply into cosmology, that a black hole is created when a star larger than our sun gets towards the end of useful life as a star, as an emitter of radiation on all kinds of different frequencies. Um, and it goes through a process called a supernova that it kind of blows up, for one of a better way of describing it. And it ends up with an extreme amount of mass concentrated in an extremely small volume, and it has a gravitational field so strong that light can't escape it, and so thus it's considered a black hole. And you can think of it as kind of a cosmic vacuum cleaner, that it will attract things that are in its neighborhood, just like the sun attracts us, or we attract them, or the Earth attracts the moon. But in the case of a black hole, if something gets too close and is not going fast enough and gets sucked in, so to speak, that it disappears inside of that black hole. So black holes can get more and more massive. Now, all spiral galaxies like the Milky Way have, by current theory, a supermassive black hole at the center that kind of holds the spiral galaxy together. But with all of the research that's been going on with dark matter and dark energy, that some other stuff's going on too that can't really describe. I bring up a black hole because current theory is that if material gets sucked into a black hole, one of the few things that is maintained is something's charge. So charge is very fundamental. Now, we all have seen a Bohr model of the atom, which is a planetary model, since we've been talking about stars and all of that kind of stuff. So the nucleus would be the center of a solar system, or of a galaxy, if you will, that has around it electrons that you can think of as being planets that are orbiting. And oftentimes you see it depicted as you see it on the screen, with these simple circular orbits. There will be a time in the future when we talk about electromagnetic radiation that pretty much nails the fact that this model is good for describing what happens chemically, but that the model is incomplete and in many ways not completely accurate, because you really can't have electrons that are moving around in these kinds of circular orbits without emitting electromagnetic radiation. And so the model falls apart, as all models do if pushed into areas where they're not best describing. But this is a useful model, so you know that electrons, those things that are in these so-called orbits, are negatively charged. And then in the nucleus, the nucleons, the things that inhabit the nucleus, some appear to be charged, and so you see the plus signs there, and those are protons, and those that don't have any electrical sign on them are neutrons, and they are electrically neutral. But like a lot of materials that exist as you are looking, like I'm looking at a table that has this or a book sitting on it, which this book, by the way, is called Zero to Maker. It's how to learn just enough to make just about anything. You can probably pick it up for about like $11 on Amazon. I highly recommend it to you. But anyways, that these are electrically neutral, which isn't to say that they don't have charges within them. It's that the charges are balanced. And so I would go so far as to assert that even neutrons are made up of charged particles. That charge is fundamental. It's just that they are ultimately electrically neutral. Now, I'm not going to go deeply into particle physics here, but the electrons are things called leptons, and they're one class of particles that are charged, that they have charge to them, and we've just defined their charge to be negative. And then those things in the nucleus are called hadrons, or they're in the family of fundamental particles called hadrons, and they are made up of even smaller items. And the items, and I'll have to make sure I try to click on the right one. Yeah, that the hadrons are made up of things called quarks. And if you're interested, that the whole history of the development of particle physics is a fascinating one. And there's a fellow named Murray Gell-Mann, or some people pronounce it Gell-Mann, took a quotation from a piece of literature called Finnegan's Wake, where James Joyce talked about 3 quarks for master mark. It's when quarks are around that they come in triplets, and currently we have that this is the royal we have some difficulty looking at individual quarks, that we have gone through and identified that there are 6 different quark, and this image shows you the 6, and each of those are paired up. So there's up down, there's charm strange, there's top bottom, and so evidence has been discovered that all of these exist, but what they have is fractional charge. And the up-down is the pair that we typically experience in the world around us. Now, as a really brief sidelight, that each of these 6 have an antiparticle that go with it, and at some point, if you look into positron emission tomography, PET scans, that you'll discover that there are things that are identical to electrons called positrons, except they have a positive charge rather than a negative charge. And so a positron is an antiparticle of an electron, and it's in the classification of what we call antimatter because it's an antiparticle. So each of these quarks also have antiparticles, but we don't experience them in any significant way in the world around us. So what I would tell you is that if you have to make up a hadron from 3 quarks, if I had 1 up and 2 downs, you would see the up has a positive 2/3 charge and a down has a negative 1/3 charge. So if I add 1 positive 2/3 along with 2 negative 1/3, you would see that the net charge would be 0. So that would be a neutron. So a neutron is made of 1 up and 2 downs. Now, again, when I say that it is made this way, this is a model. Like everything we've talked about in this course, that it doesn't, I'm not trying to tell you this is the way the universe actually is. This is a human-created model that helps us understand, and there's plenty of experimental evidence to support this model. Okay, now let's talk about a proton. If I took 2 ups and 1 down, I would end up with a positive 4/3 from the 2 ups and a negative 1/3 charge from the down, which would give me a net 3/3 or 1 positive charge. So a proton is made up of two ups and one down. And there have been some that suggest that protons and neutrons can, in fact, by quark exchange, change from one to the other, and there will be some nuclear processes that you can look at in the future where protons turn into neutrons and vice versa, which is through beta decay or positive beta decay on the other side. And again, it's the positive beta decay that allows us to have PET scans that this is not just airy-fairy out in the who gives a crap kind of area, that these kinds of things have really practical implications. But I am, with this conversation, trying to emphasize how charge is something that plays a role in all matter that we know of, whether we think it's charged or not. So, that's about as long as educational theorists would say that I can talk without you totally tuning out. So I'm done with my charge talk, so bye-bye now.